Hi, everybody. So the plan for today is to talk about R matrices. So the plan for today is to talk about R matrices, Young-Baxter equations, etc. So that's and a reminder. This is the same reminder every lecture, but that's the cornerstone of what we're doing here. So we'll what the setup is the following. We have a one-dimensional. Say we have a one-dimensional torus action. It'll be more than one-dimensional in a second. But so this is the Lie algebra, kind of the real version, the Lie algebra of some torus A, which in this particular instance is isomorphic to C star with some coordinate A. And then we think of this as if you will, a phase diagram of some physical theory where this is a parameter, this is a parameter in the real Lie algebra, and at the origin sits some x, and away from the origin sits the fixed locus here. So, and then corresponding to that, we've constructed certain correspondences, which the correspondence I will just. This is really a correspondence, but I write it as if it was a map. It's a Lagrangian correspondence. So Lagrangian correspondence, which is supposed to be, maybe I'll move it like here. So this, each of them, and this Lagrangian correspondence is supposed to be some improved version of attracting manifold. Meaning we have some inside of my ambient X. So this is my ambient X. Somewhere in it sits a fixed locus, and fixed locus may have several components, but let me draw one. So this is a component of the fixed locus. And then there is attracting manifold and the repelling manifold. And if this was the only one component, that would be the correspondence. But otherwise, we have to correct it, and we spoke at length about it. This is I apologize. This comes up every time. This is feature such a wonderful feature of Windows. And so, in particular, in this examples, what we had early in the course, this could be the situation that this fixed locus could be, for example, this could be a product of two other manifolds. We looked at these examples, and then this correspondence is acting on cohomology. Correspondences give on cohomology, meaning elliptic ordinary cohomology, K-theory, elliptic cohomology, and so on. This correspondences give maps which we should think of. Then this is some sort of vector space V with some label A1, tensor V, some label A2, that maps to some kind of space, which will just kind of denote V. And then there is a map from a different tensor product, E1, A1, tensor opposite tensor product, E2, A2. And then if the composition of this map, maybe you call this map step, and this map stop, maybe stop plus stop inverse, then the composition of this map with the inverse of the other, that's the R matrix. So the R matrix, which will depend on the ratio of N1, A2, this is the composition. And both of these maps are isomorphisms after localization. This is an actual map, but this is isomorphism after localization. And so this is some rational. These maps don't have denominators in A, but the composed map has a denominator, may have denominators in A. Okay. And then maybe here the way to maybe picture this in a more traditional way is that this is A1 and A2. They're sit in some two-dimensional torus, maybe, in which the diagonal subtorus really acts trivially. So everything depends only on the ratio of N1 and N2. And the way maybe to picture this, you can draw, that's this. We have a point in the two-dimensional torus you can think of as 2 points. So this is, we think of this as, we can think of this thing as 2 points, a couple of points in pair of points in here, and so then we have a point A1 and A2. Something special happens when they're equal. If they're equal, this is where A1 equals A2. Some special point. And then if they're equal, then these 2 points kind of vary, and they hit a point where they're equal. Then something happens, and then the R matrix, that's the R matrix tells us. So this is the way to think about this diagram, is that we have a state where these 2 points are not equal, and then there's a state in which the points are equal, and then there's a correspondence one way, and then you compose with the correspondence the other way. So that's the R matrix. So that's sorry. Okay. And then there's this, from this R matrix, what we would like to satisfy, this R matrix, we would like to satisfy the Young-Baxter equation. The Young-Baxter equation considers the situation when we have 3 points. So maybe we have a situation like this. 1, 2, 3. That should be equal, that product should be equal to this sort of product. And the way to interpret it here, that here we should think of this. So these are 2 points in C2. So 2 points in C star up to, these are, maybe we worry about them up to overall translation. So maybe here are 3 points in C star up to overall translation. So the corresponding picture in the Lie algebra would be now, so this is my A. In this picture, the torus A is something like C star cubed modulo diagonal C star. So here, so its Lie algebra is something two-dimensional, and it has a corresponding chamber decomposition. It looks like that. So this is. Then we have the fixed locus. The fixed loci look like over a point, over a generic point here sits over. To generic point here, we associate just the fixed locus of a whole torus over the origin. We have the whole space X, maybe different color, and over some other subtorus. So if I have a subtorus, A prime, then to that subtorus I can associate a fixed locus of that subtorus XA. So this is what sits on. This is what sits on the this is what sits on the hyperplanes here in this picture. And then the fact that then when I a crossing like this, so this may be slightly unfortunate choice of colors, but this a crossing like this corresponds to, so crossing here. Maybe let me choose it to a different. Let me do a different color here. I'll try to do a different color to see if it works. Yeah, it works. Okay. So if this is maybe this is where A1 is equal to A2. This is where A2 is equal to A3, and this is where A1 is equal to A3. So this crossing this wall here corresponds to corresponding 1 and 3 becoming the same in this picture here. And the fact that this 3 composition is equal to this 3 composition, well, that's the statement that if I go like that, like that, like that, that is the same as. So here is I started with A1 and 2, so this should be better stay here. So sorry. So here I first cross 1 and 2, so maybe I first cross this wall, then I cross this wall, and then I cross that wall. And here I do it in the opposite way. So I'll do it like that. Cross this wall, that wall, and that wall. Okay. So the Young-Baxter equation is equivalent to the fact that crossing these 3 walls is the same as crossing these 3 walls. And then an important point that this is the setup on this side here. This setup with various chambers in the Lie algebra of a torus is more general. Then this setup, this has to do, this is specific. This is specific to just really to root systems of type A, well, in this case, A1, A2. well, we don't really need anything more, but this is A1 is where you have the R matrix, where you have two things, and when they're equal, that then you get some interaction. That's A2 is when you have this interpretation. And generally, if you think of this, this could be some on this side. On this side here, I have the setup is that I have an arbitrary Lie algebra sum torus A, well, the real version of that. And then in this Lie algebra inside, I have some hyperplanes. And then my ability to draw some multidimensional pictures is limited. But if you want to, go one dimension up, it's easier to draw actual, like the corresponding hyperplane arrangements on the surface of a sphere, or on the surface of another solid. Like, for example, if I want to draw a 3-root system, so this should be on this side. I apologize. So it's on the tetrahedron side. On the tetrahedron side, if you want to draw a 3-root system, you just take a tetrahedron and you partition every face of that into 6 triangles. And then the corresponding cones, the cones over this triangle center the tetrahedron, which is what the picture is supposed to show behind me. So okay, I'll try. Oh, here. It's an interesting test to do it in. So this is so in general, you should imagine you have cones over some kind of collection of cones inside your Lie algebra A. Cones of, so you have cones of all different dimensions, and they correspond to each one of them correspond to some particular subtorus. So it corresponds to a subtorus for every point here. Corresponds to a subtorus. Maybe that's the Lie algebra of some subtorus A prime, and over that sits, to that you associate the fixed locus of that subtorus, and then for every pair of strata here, you associate them, in fact, 2 maps. So there is maybe let's imagine we have so here we have X at the origin, and then X here, and you associate 2 different maps. You have a map, the stable. I'll have it more colorful here. You have the stable envelope, one correspondence, and then you have the inverse. And the inverse we discuss in a second, but there's a and the so is that clear? You have you should think of this. So if I draw a corresponding if I'm in this situation, then for every strata in this picture, I have maybe for every strata of this picture, I have a map between 2 adjacent strata. So maybe let me not try to draw something very high dimensional. So let me draw still a 2-dimensional picture, but let's maybe go away a little bit for a second. Go away from the A-type root system. Doesn't have to do anything with roots. So then a fan like this you can code by dual polytope, and we'll talk about this polytope in a second. And the way this dual polytope works is that you what was cone of maximal dimension becomes a vertex, and what was a cone of minimal dimension becomes a face. So this maybe So let me undo this. So the cones of maximal dimension here, like for example, if I take that cone, that becomes a vertex, and cone of minimal dimension here, that becomes this whole face, which we'll color in a second. And then, so the vertices would correspond to. And so then for every, and this statement that for every pair, of adjacent cones here, or faces here. So this is this duality that interchanges, that preserved adjacency interchanges the size. What becomes, what the small becomes large. We have maps. Which are the, so maybe I'll do it in this language. So in this language we have, so each one of them corresponds, maybe here corresponds, this is a face of some dimension, so maybe x, a, whatever, let's, prime, and then there is a x of some subtorus a double prime, could be some any dimension. But the point is that this is the, in this situation, it's always, since they're adjacent, means a prime is a subtorus inside a double prime. And so then we have the corresponding stable envelopes going both ways. We have the stable envelope, and we have its inverse, we will discuss in a second. The inverse of a stable envelope, it's also a stable envelope. And then what is the main kind of one and only statement about this, that this form, this maps theorem, this is what the theorem is, that this form, so maybe call it lemma theorem, which is, well, maybe call it theorem, known as the triangle lemma. This maps compose, i.e. form a representation of a certain, i.e. form of the corresponding, well, you can define it to be a, you can define a groupoid with the maps like that, so this would be of the corresponding. And what does it mean? It means that if I have something intermediate, so this is adjacent. This is my picture here. So this is, sorry. So this is the stratum where I'm going, and this is the stratum where I am, and this is my stable envelope. Then I can consider, since there's an intermediate, so there is an intermediate stratum here corresponding to the fact, so this is the, so I have my subtorus here inside another torus there, and then I can have something intermediate in the middle. And then the statement is that if I take this stable envelope and I take then this stable envelope, that they compose. Okay. So this is maybe more formally. I have my x, the fixed locus for a double prime. I have my fixed locus for a prime, and here I have my a. I should have chosen a different notation for this primes, but so this is the stable envelope. This is a stable envelope for the torus, which is a prime over a double prime, and I can decompose it as a composition of things which go here. This is for the torus a prime over a triple prime, and this is for the torus of a triple prime over a double prime. Okay, that's. And so this is we'll prove it in a second when we formulate it correctly. So so this theorem needs precision. Needs a precise statement, which we'll give in a second. But before we give that precise statement, but this implies Yang-Baxter and everything. So this is because what is this? What is the R matrix from this perspective? So the R matrix is you can have so from my well, I guess I already defined our matrix here, and so then so the Baxter, and Baxter relates to again this situation which we had here, and then so maybe so in this case at the center sits the whole X. See, here sits some sub think of the corresponding to the fixed locus of the whole torus, and here is another fixed locus of the whole torus, and here is a subtorus, which we'll maybe call it. What's the color we haven't used? Well, let's pick this one. So here sits a subtorus kind of thing. And if we want to go, we can go from here to here. Means this is like, so this is one stable envelope. Maybe call it call this cone. So this maybe call it cone C plus cone, and then there's a C minus cone. And so if we want to take the stable envelope C plus and compose it with the stable envelope for C minus inverse, so this is going from here to there. Well, we can, by the triangle lemma, we might as well go a different way. We can go this route and that route, and then going back, we can come back way, this way, and that way. That says that this is the same as the R matrix computed. So what does this lemma say? It say we first go to some, not to the whole ambit space, but just to this A prime. So this is the same as computed. So this is kind of the R matrix, maybe call this thing call this to be the R matrix going from C plus to C minus. So that says that this can be computed inside this XA prime. So this is the fact. This corresponds to the fact that if we want to in the, so I'm going back here. This particular R matrix that says here, this is computed. So here we're talking about here we're talking about some, some kind of the generic fixed locus here is a product of 3 different x's, and this particular R matrix here is computed inside of just the tensor product of V1 and V3, which is the fixed locus. For the corresponding subtorus. And now this says that if I can factor with this, I can now take the R matrix going from call it. I take the R matrix is going from here to there. So this is the inverse of that. By this lemma, I can factor it in 2 different ways. I can factor this going across here, or I can factor it going across there. So that's the proof of Yang-Boxer. The proof of Yang-Boxer is that you extend everything. In other words, you prove Yang-Boxer by extending everything to the situation. So you prove that this is equal to something else by defining. So this blue thing corresponds to the case when they. So you prove that Yang-Boxer is equal. This is equal to the other side by proving that in fact you can define something where all the three cross at the same point. And then these 2 are equal, and therefore they equal to the other side. That's the argument. Okay. So now going back to the maybe I'll write this down. Yang-Boxer is proven by defining a crossing like that and showing this two, and just showing that this two equal. That's well, just draw a picture. All right. So now now about precise. Oh. I have some trouble with my audio. Not sure what's happening. Let me try to reboot my audio and see what's. Okay. Can you hear me again? So sorry,
Yeah.
I apologize. Not sure what that was. So okay. So now about precision. So precision is needed. We're going to prove fact. So in fact, we should be proving not the usual Young-Baxter, but the dynamical Young-Baxter equation. And that requires this discussion. So this will be discussed presently. And so I remind you what was the again. Let's just again so remind the setup. The setup is again. So I have my just the same kind of thing. I have this was my x. I think I'm denoting it by green today. And here was the fixed locus of some torus. And we want a Lagrangian correspondence. We want a, kind of a, so what we want. Want a Lagrangian, like a sort of a Lagrangian correspondence. Well, what Lagrangian correspondence? Also in elliptic, in fact, in elliptic cohomology between x. Well, correspondence maybe I'll write inside. X cross fixed locus. And we decided this has to be a so this would be. So what does it mean? We need a section, i.e. section of a certain line bundle on elliptic, the current elliptic homology of x cross, well, I'll just write x cross here, cross the fixed locus. Okay. And so I'll remind you, what's the whole kind of the whole point of elliptic, well, maybe not the whole point, but very important point of elliptic homology is that is that elliptic homology, we don't get functions, we get a spectrum, and then we're free to consider various line bundles. So spectrum in the sense, not in the sense of algebraic topology, spectrum, algebraic geometry, we get a scheme. And so we're free to consider sections of various line bundles, and then how big is that line bundle depends what sort of class we're going to get. So I'll just remind. It's been a while, so but let's remind you that like if I want one, like identity one, which is identity homology, which is also like the fundamental class of X, and so forth. This is a section. Well, that's an actual elliptic homology class. It's one, so it's a section of functions on elliptic homology of X, which, since we're talking about, we like theta functions. This is section of the theta bundle corresponding to zero bundle. So maybe I'll put it. And on the other hand, if we take a class of a point, kind of class of a point, that is the image of the push forward of a point. So this image, push forward of the fundamental class. Push forward of one under the inclusion of a point inside X. Remember, with push forward elliptic homology, you have to put like a normal bundle in. So that would be a section of the theta bundle of the tangent bundle of X, because if I think of the, like in the current situation, if I take a fixed point, then the class of the fixed point will be the product of theta for all normal directions. So that's like a theta section of the theta bundle corresponding to the tangent bundle of X. So this is a trivial bundle. This is a little like this is almost, this would be like the canonical of the elliptic homology if X were compact. Here we assume, of course, X is smooth. Otherwise, we talk about tangent bundle. So let's just say, so we would like this to be a complex orientable map. So this is an inclusion of a smooth point. Inclusion of a smooth point. So right, and then Lagrangian is something between the whole thing and a point. So Lagrangians, there should be sections of some bundle S, I think we denoted, which is somewhere between, which is kind of like the square root. Just kind of like the square root of that bundle. But then we decided that it's very important to allow shift by degree zero bundle times something degree zero. Otherwise, even if we saw this kind of the basic example, this is unavoidable for this very simplest reason. And the reason it's unavoidable is because even in the situation, the simplest possible situation, when we have like a vector space, X is a vector space, and if I'd like to have R matrices, so then recall that situation, we have some space with my fixed locus, and then I have attracting weight, which I denote, maybe this weight I denote Wi. These are the weights of the attracting. These are the churn roots of the attracting bundle. Of maybe I'll write the attracting bundle. You take the normal bundle in X to the fixed locus, take the positive parts, and then the dual repelling weight would be if H bar is the weight of the symplectic form, then this would be like Wi times H bar. These are the where H bar is the weight of the symplectic form of X. And so these are the churn roots of the negative part of this bundle. And then if I compute, so what will be the class of attracting manifold? Well, would be the product, be like the product of thetas. Theta function is symmetric with respect to inversion of the variable, so I'll just write Wi prime. And so these are, you want to know class of a manifold, you take the product of the normal weight of the churn roots of the normal bundle, and then I compute the repelling manifold. So that would be the product of theta of Wi. And the point of this have the node sections of the same bundle. Right? They have same degree. They differ. So they kind of, if I take the ratio, that would be, if I take something like this is not a section of trivial bundle, or we can say that this has degree 0. In the variables A inside the, well, I'll write kernel of H bar. So if I have a subtorus on which this character H bar is trivial, then this would be a corresponding variables here that has degree 0. But this is not a trivial bundle. So one has to allow a twist, even if I'm in a situation of a vector space, you would like to have attracting and repelling directions be on the same footing, that one should allow this kind of twist, and one will allow. So maybe the kind of thing we really consider is that to match this kind of, you can set this up in many different ways, but I will set it up now so that it's somehow as close as possible to existing literature. So that this is the burden of being close to existing literature is sometimes very heavy. Like, for example, I wish H bar. I wish early on we denoted H bar not the weight of the symplectic form, but the inverse of the weight of the symplectic form. That's the weight of the Poisson tensor. But anyway, that was the convention. So it's too late to change it now. But anyway, to stick to what we want to the literature, we will assume. So assume X has a polarization. Should take T 1/2 of X, which solves, so i.e. a solution to the equation. So if I take the polarization and I take the dual vector bundle, so then I have the whole tangent bundle in A-equivalent cohomology, in A-equivalent K-theory. So this equation doesn't have to be called as stated, but it's enough. So maybe I'll write it kind of. I write it. This is equivalent. The class of that. So this is in A-equivalent K-theory. And then as my square root, I can take S to be this theta bundle of half of these directions. And as a twist pi degree 0 bundle, I could take something of the form, like I call it U, and this U is for short for a bundle of the following form. So this is we discussed that at some length, but I'll remind you. So it's like a tensor product of this kind of U, Li, Zi. This is a basis in pic X, and this is a dual. These are the dual coordinates. And this is degree 0 in either coordinate, and this is has the form has a section. This has a section of the form. Well, it's not. It's going to be a meromorphic section, but it's enough to specify. So if I gave you a meromorphic section of a line by the elliptic curve, it's enough to specify it. So Si Zi over theta of Si theta Zi, where this Si is the first Chern class. This is C1 of Li. It's a core. I mean, every line bundle has a Chern class, and this is that sort of thing. And here we write the group operation on the elliptic curve multiplicatively, as we agree that the group operation on the elliptic curve reflects comes from in general group operations in like formal groups in current cobordism and so forth. It comes from tensor product of line bundles, and so it's very good to write elliptic curve multiplicatively, because this various computation in K-theory, they go verbatim to computations with elliptic functions. Because in K-theory you have operations of product and sum, and this would just interpreted the directly interpreted in terms of elliptic functions. So that's the thing. And then so if I have a fixed locus has. So if I have a fixed locus has its own polarization. Namely, when a polarization of a fixed locus, what you do is you take the polarization of X, you restrict to the fixed locus, and you take the fixed components. But in addition, has something one might call index. Namely, you take this polarization here, you can write as a sum, kind of a fixed sum. Well, you can write it as a fixed plus attracting plus repelling. In general, you can decompose, once you have a K-theory class, you restrict those fixed locus, you can decompose it according to the characters of the group. And so in particular, you can recompose it to attracting, repelling, and so on and so forth. And so this would be, if this index is the determinant, that's the determinant of this attracting part. So you take T1 half, restrict to the fixed locus, and you take attracting part. So if your X was a cotangent bundle to something else, and the polarization, so this is if X, maybe I'll write it here. So if X is T star of M, and the polarization of X, well, it's just really the tangent bundle to M. There's 1/2 of the tangent bundle to X. Then this would be the usual, it has to do with the usual index of a fixed point. So, how many attraction directions it has. So, and so then the stable envelope where does it go? It takes, so what we would like to have, we would like to get a section of S on X. So you can, when we talk about Lagrangian correspondences, you can talk about what there are as sections of line bundles in the product, but you can also maybe easier sometimes to talk about sections of what they map to sections of what. So we're going to get, we want sections of S on X. And then the source of this map, so we start, so this is the target. Target has to do with, so this is the target. And in the source, we take kind of take SA. Just write SA. But then what is this SA? This SA is the theta function of the theta bundle of the polarization of the fixed locus. Tensor this U restricted to my fixed locus, this I can do. So this, if I have a fixed locus, I have a fixed locus, I can restrict any, if I have fixed locus, I have inclusion of the fixed locus into ambient space. In particular, if any line bundle on the elliptic homology of the ambient space, I can restrict it to the fixed locus. But then this here, so this has to do, but this is now gets shifted. So maybe, so this is now shifted. By the variable Z become Z minus H bar times this determinant index. So maybe, sorry, maybe you should call this index, I apologize. Let's talk the index, not the determinant, but the actual thing. The actual vector bundle. Where? What's the determinant index? That index, this is a line bundle on the fixed locus. On the fixed locus. So an element, i.e., an element in pick pick of a fixed locus. This is a co-character. So a co-character of the torus pick x a tensor c star. This is where the variables. This is where the variables. Well, these are called scalar variables. That live for the fixed locus. For the fixed locus, so the x, so in other words, x has some, so maybe I'll write it like this. There's some variables z that for that these are the variables for x. So this would be this variable z sit in like pick x tensor elliptic curve. If I have an inclusion of the fixed locus, I have a pullback of a line bundle. So this thing will map. So by pullback of line bundles, this will map to the corresponding. Well, now for the fixed locus, I'll draw a less concrete picture. So this would be. So in principle, could be surjective, could be. This map doesn't have to be surjective or objective or anything. It's just some map. So its images could be something like that. So this will map to something like that. Could be, like I said, it could be surjective, could be injective, could be neither. Something. But then here, this the variables. This is where the variable z for the fixed locus. The fixed locus live in pick the fixed locus. Tensor elliptic curve, and there's some map. And this map we're now going to shift by what? We're going to shift it by this map. We now shift by this determinant index. So there's a shift by that index, sort of applied to h bar. H bar sits. So this is a co-character. We have a co-character, then you can plug in a variable there. So this is the co-character of a torus. So this is a co-character. Plug h bar into any co-character. In particular. So that's the map. So the map goes from, if you want to get a section of a specific, section of a specific line bundle in X, you have to write a specific line bundle here, and that line bundle is more or less restriction from X, corrected for that index. And so now the triangle lemma now reads, the way the triangle lemma now reads is that I have my, so maybe not, maybe the triangle M I'll just draw. Well, you know, it's how the easier to, what would be easier for you to understand, but let me see. So now again, for every piece of my picture, I have my X here. So I think it was in green. So my X here, and it has this line bundle where I want to end. Right? And then there's a source, fixed locus, and then there is this S for the fixed locus, but it's shifted by minus H bar Z int. And now if I want to go intermediate, then okay. So here I have an intermediate stop. Maybe there's some intermediate torus. And then if I'd like from this intermediate torus to get here, well, I can have to shift it by an amount which is determined index. Maybe I'll just write an index, where index of what where. So it's the index. I'll write x slash x to fixed locus. So this has to do with I take polarization of all x and restrict it here, and then here would be the determinant of the index. And now I have to take, so but now it's only x over kind of this larger fixed locus. Right? Okay. And so now the lemma should say that this triangle commutes. So if I could go here, there, and there, that should be a commutative triangle. So the triangle, and the reason it commutes by uniqueness of stable envelope. When we discussed stable envelopes, there's some work to prove they exist, but the fact they're unique, it's an easy fact. And then anyway, you have a map that has to be unique, except one has to think about what is that arrow. This arrow here, what's the color which is not used in this picture? Maybe this arrow here. This arrow here is the stable envelope. For the fixed locus of that inside of this fixed locus, but this is shifted. The stable envelope is shifted. Really, it's you know, there's some shift of variables here, and that shift of variables is explicitly written here because we go to a source. So this is for this we label stable envelopes by the target where we want to end, and here the target is explicitly shifted by exactly this amount. By exactly that. Okay. And so in particular, when you write the Yang-Baxter equation, this will have, so in particular, Yang-Baxter equation will have explicit shifts in Scalar variables, also known as dynamical. Okay. And maybe, so this is, you can, as an exercise, you can write it out and check that. So maybe it's a good exercise. So good exercise, write it out for an academic writing. For, well, if you don't know the academic writer, you can do T-star Grassmannian or general academic writing. See that you really get the usual, so this maybe the usual dynamical Yang-Baxter equation. I want to talk about something else here, and namely, so is namely, say exact same thing, but now in a dual picture. In a dual picture is that, so here we had how I imagine, so dual, not in the sense of profound duality, but in the sense of just in terms of polytope. So if I take this kind of dual polytope, now how should I think about that polytope? So this polytope here. So these are the, after all, so this is everything is happening in the Lie algebra. So these are the, so this happening in the Lie algebra of A. And so the dual polytope really belongs, really sits in the, where it sits, where it really sits, is in this thing. It really sits in the dual space, because in vector space and the dual vector space and the duality of stuff, it really sits in the dual. So I'll just write this guy sits in the dual. So this has to do with weights. In other words, it has to do with weights of some representation of A. And what are these weights? These are the these hyperplanes is where some weight, maybe call it W, of A equals equals 1. I write it in multiplicity notation, but draw a picture in Lie algebra. I hope you forgive me. Where what? So these are the weights. So these are the normal weights where these W's are, where these W's are the normal bundle. Where these are the weights in the normal bundle to the fixed locus, right? And then the dual polytope, this is, if I have, imagine for a second I have just a vector space representation. Then that this dual polytope is like the Newton polytope. For the exterior algebra of, so I haven't anchored it anywhere yet. It's just kind of floating in the dual space for the exterior algebra of the space, right? Because if I take, so if I have like here, if I have maybe do an example here. So here, if my weights are the, so let me do an example. In fact, let's do this very example. So maybe I'll pick. So we're going to be talking about symplectic representation in a second. So in symplectic representation, of course, with every weight there's an opposite weight, and this is why we have polarization and stuff. But let's just pick three weights which are perpendicular to the stuff we have here, like that, right? So these are three perpendicular weights, and if I take the exterior algebra is the projection that is going to be you have to project a cube. So this would be the weights, the Newton polytope exterior algebra. So the weights that appear in the exterior algebra, this is the projection. The weights that appear in the exterior algebra is like some kind of cube of some dimension, because every weight, when you take an exterior algebra vector space, every weight you either include or don't include. So projection of a cube of dimension equal to the rank here, with the where the generators. So I should be able to draw a cube. So I have a cube, some dimension. So the basis vectors of that cube should go to my three vectors there. So maybe I'll just, so these three vectors go to that three vectors. And so that would look like, so this is fun to draw. So this is projection of a cube called a zonotopes. And it has kind of nice. So this would be, it'll be tiled by, so this would look like that. Right, and then it's exactly this six-gon that we're talking about here, right? So, but now you should remember. So this is, that was we're going polytope, and that polytope. So this is when we cross various walls, we in fact go on vertices of some polytope, and this is the polytope. So this is the polytope in which we're going. And then, but then you should remember that this space. These are weights, but they're in fact projections. But really, they're Chern roots. They're not just weights. They are Chern roots of a bundle. Right? And so that clear? In other words, they have a coordinate. In other words, they have a coordinate. This zonotope In other words, i.e., the zonotop lives not just in the dual of the Lie algebra, but in fact in equivalent pick, the fixed locus. So this is the when we talk about what's the like the smallest and what's the largest way that appears. So when we talk about, for example, when we talk about like this component and that component here. So maybe that's not the best picture. Let me draw one more picture here. Then we can, if we pick a particular chamber, maybe pick this chamber here. Then what are the largest and the smallest ways that appear? The largest way that appear is, so this is the largest way that appear. That's you take the top exterior power of the attracting part. Oh, right. Sorry, I forgot to say. Yeah, I apologize. Since here we have a symplectic representation. So with every weight, there is an opposite weight. So there is an opposite weight here. And then between the two, we choose one. In polarization. So instead of taking the Newton, if I take the whole normal bundle, I'll just get a polytope which is twice the size, because if I take a cube twice the size and project it, I'm going to get a polytope which is twice the size of the zonotope. And so this would be, instead of having the whole normal bundle, I'll just take the polarization of that. That would be more economical. So if I take that polarization, then the largest thing will appear is I have to take this polarization and I have to take the top exterior power of the positive part of that, and the smallest thing will appear. This would be the top exterior power of the repelling guy. Right? But then more generally, if I have a polytope of kind of, and I don't need this interior things. So, but in general, I have some polytope. Then at every facet of that, polytope, I have at every facet of that polytope, I have like, where is that facet? The way that facet sit, if I have some facet here, this corresponds to this corresponds to measuring weights with respect to subtorus. So maybe there's a dual to weights with respect to subtorus A prime. And then here I go between the top exterior part of it, take the polarization, you take attracting with respect to this A prime, and I go between the top exterior part of polarization and take repelling with respect to A prime. But now I keep stressing is that this quantities, they're not just these are not just weights. This is the top exterior power of some vector bundle. These are also elements of the covariant peak of the fixed locus. They have some line bundle in them. So these are not just weights, so they're just really line bundles. That's what I'm trying to say. And so when we write our R matrix, like remember we keep drawing this picture today, we would like to cross a wall like that. Then in this picture, this corresponds to going along this segment here. That's my little picture. So this goes from sorry, this would be the starting point, and this would be the end point, and then we go from here to there. And as we go there is a shift, and we shift by this. So this is the index by which we have to shift. So this R matrix is not, in other words, this space has some kind of origin, and this transformation is not just the R matrix. This guy is not just the R matrix for the fixed locus AA inside the fixed locus A prime. It has to remember it remembers the ambient geometry. Interesting typesetting on my part. So it remembers the ambient geometry through precisely this shift. So it sits in an ambient space. In an ambient space, there are some directions with respect. So this is A sits inside a fixed locus for A prime. All the directions are fixed by N prime, but in the ambient space, there are directions which are not fixed by N prime, and it's a line bundle in N prime, and it's exactly shifted by exact this amount. This object is the dynamical shift. If you write it like this, it makes super clear sense why it should be there, because if you go around that polytope, nobody said that if you go around the polytope, nobody said that this is like this shift and that shift have to be. So our polytope is a zonotope. It's always centrally symmetric. Every face of that is centrally symmetric. But this transformation from here to here, this, if you go around this side, or if you go around that side, going here, this is almost the same, but not quite. And this has to do with precisely the shift of the scalar variables. And this is and what the scalar variables record is well, you should think, like I said, you should think of that polytope around the various facets of this which we go as having coordinates not just where it sits, not just in weight, but having, in fact, it being a projection of something that sits in peak. And as you go around, a certain path, you have to remember that. And okay, so this is I'm running out of time for today, but let me draw analogy here. Is that the analogous? There's a completely analogous. So we talked about some time ago. We talked about things like three-dimensional mirror symmetry, and then there's a certain interchange between the Scalar variables and the covariant variables. And so if you do the same for the Scalar variables, these two spaces will not even be the same spaces. They will differ by a flop. And so the fact, like by a full flop. And so that means it stands to reason that so even though your polytope is centrally symmetric, and every face of that is centrally symmetric, going around different edges or across different faces of that polytope is not exactly centrally symmetric operation. As you do the central symmetry, you have to remember how that polytope was sitting in there, such a shift. Well, maybe I conclude by noting that these 2 points, while these things are kind of, this is really determined. This is determined, or maybe depends on ambient geometry. Situation. That the difference between them, this distance, by how much you differ, by how much you go, this distance is independent. So this is difference between these two shifts. This difference is fixed by topology. So this is, in other words, this polytope. What is not fixed is where. So maybe I'll make this point about the actual weight. Like the actual weight, if I want to know, forget the peak. Just think about the actual weight. So if I choose different polarization, this point will move and this point will move, but the size of the polytope is always the same. The actual size up to translation. So up to translation, this polytope. So the polytope. In other words, the polytope is fixed by topology. Means it's a polytope of a fixed shape, and if I choose a different polarization, it's going to move around a little bit, but it's not going to change its shape. And then similarly, this individual shift, might go up and down, but the difference is always the same. Well, okay, so this summarizes the dynamical Yang-Baxter equation, and sorry we're going a little slower than I was planning to, but whatever. Such is my ability to progress through this material. Are there any questions? Not a single question today?
I have a few questions actually that are
sure
from a bit back. So first, I didn't really get why the class of a point should be a section of the Thom bundle of like the tangent space.
Oh yeah, sure. So this is okay. So then let me explain that. So if I have a map between let's say y mapping to x, so map f, then push forward elliptic homology goes, you take the minus the theta of the normal bundle to F going to O. So this is where they kind of push forward. Good. But then if you have, so this is how push forward is defined. But then if you have any bundle V on X, you can just twist it by the theta of V, and you're gonna get theta of minus the normal bundle of F plus the pullback of V going to O of sorry, not O, theta of V. So in particular, if it is the case that this bundle is trivial, then we get a section of theta of V. So if we have a manifold such its normal bundle is a pullback, so if we have submanifold in X such as the normal bundle is restriction of some bundle of V. So in other words, so if my normal bundle to the point is restriction of the tangent bundle, so e.g. so here we have for now Y is a point, V is the tangent bundle of X, then we're gonna get O here mapping to the theta of tangent bundle of X. That helps?
Yeah, that's very helpful. Thank you.
Sure.
And the second thing that I didn't really get is when we were twisting by get end, what like defines the bundle that we're twisting by? Like, how do we know what it is?
Well, it's some line bundle. We don't know what it is. It's so again, let's go back here. We have some polarization of X, and when we restrict it to the fixed locus, we get as a fixed part we get the induced polarization of the fixed locus, but then we get some attracting and repelling bundle. In fact, we can decompose this into all these bundles. We can break further, attracting and repelling. We can decompose further by characters of the fixed locus. But in general, those are just some line bundles some vector bundles on the fixed locus. And then if we take a determinant, they're going to get some line bundles.
Okay, I see. Thank you.
Sure. More questions? Like in this picture that I keep drawing. Where was that picture, right? That picture, you should think of it. Well, I denote them WIs if they were weights of the torus, but in principle they're Chern roots. I mean, each one of them is some Chern root of some vector bundle, and so that vector bundle might very well be non-trivial. Maybe anything you want somehow. Other questions? Well, if there's no further questions, then to be continued next week. Thank you so much.